All right. There we go. Perfect. All right. And you all should be able to see my notes. All right. Excellent. So I'm just going to keep my video off for a little bit to help with bandwidth. But let's just go ahead and talk about pathophysiology. So when we say pathophysiology, what do you all think? What is pathophysiology? And more importantly, what differentiates pathophysiology than, say, anatomy and physiology?
Because we're focusing specifically on pathogens.
Maybe pathogens might be a part of it.
You're understanding how the body reacts to the disease.
How the body reacts to disease. Good.
To me, pathophysiology is more in depth into a cellular level on how the body works and how just a little chemical imbalance can throw off your normal ways.
Okay. All right. So I think we're moving in the right direction here. So let me ask you all a question. What does ology mean? What does ology mean?
The study of.
Yeah, so ology is the study of something. And what is physiology? And that harkens back to anatomy and physiology. What is the physiology component of anatomy?
Body system.
Maybe.
Physical composition.
Composition, maybe. So when we say anatomy, what is anatomy?
Pertaining to a specific part of the body.
Oh, say that again. I got a little feedback there.
Pertaining to the specific part of the body.
So maybe a specific part of the body, yeah. Or what we say in medicine is anatomy is the study of the structures. Or as you said, parts of the body. So we'll look at the liver, or we'll look at a bone. That is anatomy. And then physiology is a little different. So physiology isn't so much looking at the overall structure of something, but rather it is looking at what?
Its function.
Yeah. So physiology is the study of the function. And then collectively, anatomy and physiology is the study of the structures of the body and the function of those structures. Whereas pathophysiology, so physiology is the function. And what does path mean? What does path mean?
Disease.
Disease or disordered? Good. So pathophysiology is the study of disordered function. So it is looking at the function when it is gone wrong, essentially. So anatomy and physiology is more about what's the normal function and what are the normal structures, whereas pathophysiology is now saying, okay, now that we kind of know how things normally run, how they normally look, we want to now look at what happens when they're is abnormal function. So that is what pathophysiology fundamentally is. It's the study of abnormal function or disordered function, if you will. And so that is where pathophysiology kind of goes a little above and beyond anatomy and physiology. Is like, okay, what happens when things go wrong? So when we talk about understanding the biological world, which is an incredibly large question, there are essentially two different ways that we can figure this out. And of course, this all falls under a larger umbrella of something called the scientific method. And I suppose I should just mention that because that's really where all of this fundamentally comes from. We're going to talk about the scientific method like it's a real clean, easy to use toolbox, but it's actually quite a bit messier here. So this is just more conceptual, but it kind of gives an understanding what the scientific method is. So the scientific method is what we call it's a systematic method. And does anyone know what systematic means?
A structured approach.
Good. It's a structured approach. So you're doing something that you're taking the same approach every time. And this is important because in healthcare, in medicine, we tend to do things systematically, right? When you assess somebody, for example, right, head to toe, treat as you go, we tend to take a systematic approach and we do it the same way every time. So we don't forget something or we don't make mistakes. And so scientific method is a systematic way of figuring out how the natural world works. And so essentially what happens is we see something, we observe something, we make an observation, and we go, huh, that's interesting. Is there any way I can explain that or predict that? So you observe something, and then you research and study as much as you can about that observation. And then based on that research and study, you develop something called a hypothesis, right? And then what you do is you want to determine if that hypothesis is a good explanation for the observation. And so what you have to do is you have to develop tests. You test the hypothesis, right? This is sometimes referred to as falsifiability, right? So in science, your hypothesis has to be falsifiable. That is to say that you actually have to be able to test it, right? So let's say that I observe, right? So I have a tree here, and I observe an apple falling out of that tree, okay? And I develop a hypothesis that says that there is a ghost. Okay, there's a little ghost that came and pulled that apple. All right, there's a ghost that came and pulled the apple down. And that's my hypothesis, the ghost hypothesis. All right. Now, is that a legitimate hypothesis? Well, maybe, right? We can't discount it outright. We have to ask the question, okay, how do I test this ghost hypothesis of yours? Is there some test that you can develop that will either falsify, show that the hypothesis is not good, or will provide evidence that supports the hypothesis, right? And so I start asking questions. Well, how can we do this? Is there some way I can observe this ghost? No, the ghost is invisible. All right. Well, can I observe it with other equipment maybe, or maybe I can, use different techniques? No, there's no possible way you can observe that ghost. Well, maybe that ghost has some other effects that I can observe. No, completely invisible. I'm the only one who can see the ghost. Nobody else can. You just kind of have to take my word for it. At that point, that hypothesis is not falsifiable, that there is no test that we can do to either support or deny the claims of hypothesis, right? And so at that point, that hypothesis falls outside the realm of science. It may be something else. It may fall under the realm of some other paradigm, but it's not scientific. It's not science because we can't test it. We can't subject it to falsifiability. But on the other hand, if there is some test that you can develop, you can run that test, and then you can make additional observations that either support or refute the hypothesis. And then you just do this over and over again. And so the cool thing about science is that there is no such thing as proof. We often hear people say that, but that literally does not mean anything in science, right? There's no such thing as proving. You can disprove, but you can never prove, because there's always a possibility that some new test could come along and could falsify that hypothesis. And a hypothesis is strong enough, quote unquote, and it explains enough, and it passes multiple tests, then that hypothesis might eventually become what's known as a theory. And a theory is the strongest explanatory model that we have for something. Even a theory can be wrong, though, right? And there might be some test that can disprove a theory, if you will. So you can never prove anything. There's always a chance that we could be wrong. But the more tests you do, and the more evidence that supports the hypothesis or theory, the stronger it gets, if you will. And so this whole scientific method is what's used to help us understand lots of things, to include things in the realm of pathophysiology. And essentially what we do is we can take what's called a top-down approach or a bottom-up approach. And what do I mean by that? Well, what I mean by that is there are various levels to understanding biology, and this is sometimes referred to as the organization of life. And so we can break this down and build it up. And so we can start at the very fundamental building blocks, right? We can ask the question, okay, what are the building blocks of life, of biological systems? And essentially, it starts at something called the atom. The atom is kind of the fundamental building block of everything biological. And then what we do is atoms can come together to form what are known as molecules. All right. And then you have molecules. Molecules can come together to form more complex molecules, and these are known as macromolecules. All right. And then macromolecules can come together to form what's known as a cell. All right. So a cell is a complex system of macromolecules. And then you have multiple cell types, 2 or more types of cells that perform a similar function come together to form what are called tissues. And then 2 or more tissues come together to form what are called organs. All right. And then 2 or more organs come together to form what are known as organ systems. And then finally, multiple organ systems come together to form the organism. So we can take a bottom-up approach where we start at atoms and we go, well, let's study atoms and how they form molecules and macromolecules, and that'll help inform us about the biological system. Or we can start at the organism and we can look at the organism as a whole and then break it down and, okay, well, let's study the organ systems, and then let's study the organs, and let's work our way back to atoms, right? And so that is the top down from organism down to atom, and bottom up from atom up to organism. And there are different disciplines that look at these various concepts in detail. So for example, the discipline that looks primarily at atoms and molecules is what we call chemistry. All right. And if we're talking about the biological systems, there is a subfield of chemistry called biochemistry, right? And then what you get is you actually get crossover, right? So there's another field that kind of looks at molecules and macromolecules, and this is referred to as molecular biology. All right. And then you have a field that looks at the cells. This is called cytology, right? And you see there's a little crossover there. And then you have a field that looks at tissues with some crossover. And we call that histology, right? And then you have fields that look at the organs and the organ systems. And these include things like neurology, right? The study of nervous tissues, organs, and organ systems, or cardiology, right? Study of the cardiac and cardiovascular system, gastroenterology, right? Or pulmonology. And then finally, the organism. And this is really where we enter the picture as paramedics. Right? We interface the organism, the whole individual human being. And what we have to do is, as we're assessing that patient and we're trying to figure out what's going on and trying to develop a treatment plan, all right, we have to pull all of these other fields. We have to pull from chemistry and molecular biology and cytology and histology and neurology, cardiology and gastroenterology and pulmonology and so on and so forth, right? And we have to pull the knowledge that we have together to form something called a differential diagnosis. Now, let me ask a question for you all, and we're going to take our first break here pretty quick as well. Can we diagnose as paramedics?
Legally, no.
Is that even?
No.
Yeah, legally, no.
No?
You can treat what you can possibly see.
Okay. Well, let me ask you all a question. What is a diagnosis? When I ask a question, what is a diagnosis? Like, what is the definition of a diagnosis?
The definitive event that's happening, possibly.
Okay. So let me just get down here and
It would be
diagnosis.
the identification of a nature of illness or other problem by examination and symptoms.
Oh, somebody looked that up in the dictionary, huh? So that is correct. That is the literal definition of diagnosis. And so somebody who's saying, well, it's definitive, right? Diagnosis is definitive. The literal meaning of diagnosis is the identification, okay, of the nature of illness or some other problem by examination of signs, symptoms, history, physical exam, etc. All right. So let me ask you all that again. Do we diagnose as paramedics?
Yes, we do.
Yeah.
Yes, we can.
We do.
It'll be a field
Uh,
diagnosis.
We diagnose. I don't want you all to. I'm not very keen on saying what's your impression of the patient or what's your field diagnosis of the patient, et cetera, et cetera, et cetera. We are diagnosing as paramedics. And in fact, that is also what our medical director, Dr. Benjamin Diven, will also say. We diagnose as paramedics. Now, we don't do, right, we don't go into the chart and we don't type in the ICD-10 code, right, with a billing code, right, in the hospital when somebody gets a diagnosis. There's a code attached to every a diagnosis in the ICD, ICD-10. We don't do ICD-10 diagnoses for billing for insurance, Medicare, Medicaid, but we diagnose nonetheless. And really, a diagnosis is just, what do I think wrong with this patient, right? You have to diagnose. Otherwise, the concept of treatment makes no sense at all. And typically what we will do is we'll develop what's known as a differential diagnosis, or a DDX. And this is a list of problems. Rarely will you just look at somebody and say, I know exactly what's wrong with them. Generally, it's going to be a list of problems. And then as information comes in, problems on that list will become more or less likely. You might not ever rule anything completely in or out, but things will become more or less likely, right? And it is the ability for us to use pathophysiology, all these other disciplines, to bring that information in and to develop a diagnosis, right? What's wrong with this patient? That's really what pathophysiology is all about, is giving you some tools to better figure out what is wrong with this patient. If I understand disease, then I can better understand or better develop a way of thinking about how do I figure out what's wrong with this patient. And then once you figure out what's wrong, then we can develop a plan for treatment. And so that's where we're going to start our journey into pathophysiology here, is we're going to start talking about these different disciplines. And today we will start with chemistry and move into molecular biology and understand the foundation of all of this. But we've been going for quite some time. So what I'm going to do is I'm going to put you all on a break. Are there any questions before we take a break? First of all, anybody have any questions?
Sir.
No, sir.
No, sir.
All right. Well, let's go ahead and take a break. It's 9:46, so let's take a good one. How about we meet back up at 10 o'clock? We'll take a good solid break. I'll see you all at 10 o'clock.
Sounds good.
I guess it'd help if I would record that. We were really starting to figure some things out, and we were making some observations that were really interesting. And I'm just going to talk about a couple of these observations. So first, one of the major observations that we were doing, and we've known this for a while, is if I took some gas and I put that gas into a tube like that, maybe some hydrogen or some helium or some oxygen or something like that, and then I put an electrical potential across it, right? So maybe you have positive on this side, negative on this side here, basically hooked it up to an electrical circuit. What would happen was the gas would get excited and it would begin glowing inside of that tube. And so it would begin glowing and it would release light. And then what we would do is we would take a prism or a diffraction grating, and that we would allow that light to go through that prism or that diffraction grating. And what would happen was something very interesting, right? So that light would go through, come on, there we go. The light would go through, the light that was given off would go through that prism or that diffraction grating, and the light would actually be broken up into very specific colors. And so there would be maybe a very specific color of red that would come out, and maybe like a purple would come out, and then maybe a real light blue would come out, something like that. So we would break the original color that was coming off of this glowing excited gas into individual colors. And when it comes to light, the interesting thing about light is that color, the color of light determines the energy of that light. And the way that it works is light that is red has lower energy than light that is blue. So red light is lower energy, blue light is higher energy. And then when you go even lower in energy, you get very long wavelengths of light that you can't even see with your naked eye, and that is what we call infrared light. And then even lower energy light is what we call microwave light. And then the lowest energy light are what are called radio waves. And we cannot see those. And then likewise, light that is higher energy than blue that you can't see is what we call ultraviolet light. And then light that's even higher energy than ultraviolet light is what we call X-rays. And then beyond that are what we call gamma rays, right? So light that we can actually see is what we call the visible spectrum, right? And so what we realized by doing this is that there's something going on inside of these gas, whatever makes this gas up, right? The particles of gas. There's something interesting about their structure, and whatever's part of their structure has very specific energies associated with it, right? And when you excite it, you can break the light up into very specific energies depending on the wavelength of light. And that's called the emission spectrum. And in fact, every single element, and as we're going to learn, an element is a specific kind of atom with specific properties, but every single element has its own spectrum. When you excite it, it emits light at very specific wavelengths or colors. And you can determine these actually act as a sort of fingerprint, if you will, for each element. This is actually how we can tell, like when you hear the news and they talk about, well, we found some star and we know that this star has more oxygen inside of it than other stars. How do you know that? You know, it's hundreds, thousands of light years away. How do we know that? Well, we know that by taking the light from that star, putting that light through a prism or diffraction grating, breaking it up, and you get these different spectra that come out, and you can go, oh, look at this. This is a fingerprint for oxygen, and this is hydrogen, and this is helium, and the fingerprint is more pronounced for oxygen. And so there's more oxygen there, and that's how we can tell. Or like when we look at a planet and we go, hey, there's lots of methane in the atmosphere of this planet. We can determine that by looking at the light, right, that's coming from that planet into our telescopes and breaking that light up into its spectrum and figuring out what elements there are in the atmosphere. So that told us something. There were also other experiments that were being done. We would take that excited gas and we'd poke a little hole in the tube, and plasma would shoot out of that. And what we would do is we would take that plasma and we'd have magnets, or not magnets, but charge. So you'd have something that's really positively charged and something that's really negatively charged. And that plasma would flow through, and you would get a splitting of that plasma, right? So what you would get is you'd get a lot of it would get bent toward the positive charge, and a little bit of it would get bent toward the negative charge. And so we realized, there's something about this gas, whatever it's made of, right? Some of it is attracted to positive charge, and a little bit of it is attracted to negative charge, right? And whatever it is, it has some very specific energy associated with it. And then another experiment that was done was we would take an element that was radioactive and it would emit what are called alpha particles. And we would take a super thin sheet of gold foil, almost microscopically thin, and we would fire these alpha particles at that foil, and typically the particles would just shoot right through the gold foil. And that told us that the whatever this stuff is made of, whatever the gold is made of, is mostly space. It's mostly empty space. But every so often, what would happen was one of these alpha particles hit that gold foil, and instead of just passing right through it, it would bounce right back, it would just bounce off the gold foil. And for the most part, the alpha particles would just blast on through it. But every so often, like 1 out of 160 or 170,000 particles would bounce right back. And so they realized, okay, whatever is going on here, there's a lot of empty space, but there's something very massive in the middle, and these alpha particles are smashing into it every so often, then coming back. And so when we kind of took all these experiments together, we kind of began to realize that the general structure of an atom is that there is something very, very tiny and massive in the center of the atom called the nucleus. So it's very small and massive. And then around the nucleus, there are spread out, there are some other small particles, and that became kind of the general structure of the atom. And then we've refined that, we've done more experiments, and then quantum mechanics came about, and we finally have kind of come to our contemporary understanding of the structure of an atom, and it kind of is as follows. There is a nucleus, and that nucleus contains 2 different types of particles. These are very tiny, but they're also very massive. And there is a particle that has positive charge. That's called a proton. All right. And some nuclei contain other about equally massive particles that have no electrical charge, called neutrons. And then contained within very specific energy levels around the atom, very specific energy levels, there are tiny negatively charged particles called electrons. All right. And the protons are positively charged and the electrons are negatively charged. And what do we know about opposite charges in nature? What do we know about opposite charges in nature?
Opposites attract.
They repel each other.
Opposites attract. Opposites attract and likes repel. So the negatively charged electrons outside of the nucleus are attracted to the positively charged protons. That's what we call an electrostatic attraction, and that's what holds the atom together. These electrons are attracted to the protons, and so the electrons move in and they want to be close to the proton, but the electrons are consolidated or constrained to very specific energy levels. And when we say that something has a very specific value, that is what we call a quanta, right? There's a very specific value that is associated. And that's actually where the term quantum mechanics comes from, is by looking at the structure as, right? Now, another way of looking at this, what we're not going to go into detail here, is that this, like these little particles, is actually not completely correct. They're more like waves, and they're more like little waves of probability. And so when I draw this picture, like this little electrons, like a tiny little ball that's rotating or orbiting around the nucleus, that's actually not the case. The electron is kind of spread out around the nucleus in a wave, but it's just easier to conceptualize these tiny little point particles. That helps understanding later on when we talk about how these interact, the actual chemistry. But this is just kind of the basic model. So the basic model of an atom is you have a nucleus where most of the mass is contained, right? So a proton is like 2,000 times more massive than an electron, right? So most of the mass of an atom is in the nucleus, and electrons are like 1/2000th the mass of a proton. And the neutrons are roughly as massive as protons. So most of the mass of an atom is in the nucleus, all right? So that's something to know. And these electrons, okay, inhabit specific energy levels in an atom, but their exact location is not known. Only the probability. What's the probability of finding something if we take a look, right? And these specific energy levels are sometimes referred to as orbitals. Orbitals or shells sometimes. Not orbit, not an orbit like a planet orbiting the sun, but an orbital, which is a spread out cloud of probability at very specific energy level. And these energy levels vary from element to element. And what people started doing, Mendeleev actually was one of the first people that did this. He was a Russian in the 1800s. He started making a table of elements, starting at the lightest and then kind of stacking them up to the heaviest. And the table that emerged from that is something called the periodic table of the elements. And that's what we're looking at here. And I do have a periodic table of elements loaded into Canvas for you all. All right. And the cool thing here is this helps us, this gives us an idea of the basic atomic structure. So what you have with the periodic table of elements are you have rows and columns. So let me zoom out here. So rows and columns. All right. So a row is horizontal. Oh, it's not letting me draw. I'd like to draw on top of that picture, but it's not letting me. Okay, well, let me, that's a bummer. All right. Just do that. All right. So you have rows. These are horizontal. And then we have columns. These are vertical. All right. And a row is referred to as a period. And a column is referred to as a group. All right. So if we go back to our other note here, you see that the periodic table of element has 7 rows, essentially. Period 1, 2, 3, 4, 5, 6, 7. Everyone see that there? All right. So you've got, I wish it would let me draw on it, but it's not going to. But hopefully you all can see that. Why won't it let me draw on it? Hey, there we go. We got something. So you got rows. So there's period 1, period 2, period 3, period 4, 5, and so on and so forth. And then you've got groups, right? Columns, group 1, group 2. And then what I want you to do is I want you to forget about this middle for the time being. And then we're going to get rid of the 1 here and 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 the 1 here. That'll help simplify it. So I've got group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8. All right, everybody see that, hopefully? All right, excellent. So now what I'm going to do is I'm going to talk a little bit about how this comes together. So when we look at the periodic table of elements, you're going to see some basic information on that table. All right, so when we look at an individual element, which is an atom with specific properties, you're going to see something that looks like this. And then you're going to have a whole value number, and then you're going to have a decimal. All right, so let's break this down. So this is what's known as the atomic symbol. Right, this is just a shorthand for the element. So an H like this would be hydrogen. For example, He would be helium. Na stands for natrium, is sodium. Sodium is the contemporary term for natrium. K is potassium. C is carbon. N is nitrogen. All right. Pb, big P, little b, is plumarion. And the contemporary term for plumarion, that's where the term plumber comes from, is lead. Right. And the original pipes were made of lead, and people that would work on those pipes were known as plumbers because of plumarium was the term for lead. So that's the atomic symbol. Now, this whole value number here is super important, and this is what's called the atomic number. And the atomic number, this is critical, is the fingerprint for every element. And the atomic number tells us how many protons. So the atomic number is how many protons are there in that atom. So every atom of hydrogen will have 1 proton. That's what makes hydrogen hydrogen, 1 proton. If it has 2 protons, it's not hydrogen, it's something else, it's helium, right? 3, then it is lithium, right? So that is the fingerprint, the atomic number. It's the number of protons. And so if there is 1 proton, we know that protons are positively charged. How many electrons are there going to be? What do you all think?
One.
One, yeah.
One.
So in nature, yeah, you gotta have a negative to balance a positive. So if I look at if I look at hydrogen in nature, it has one proton in its nucleus, which means there will be one electron to balance that out. All right. So that's why the atomic number is so critical. It tells us the number of protons, and it also tells us the number of electrons in nature. Everybody okay there? All right. So the way this works is when we talk about chemistry, the interaction of different elements. All right. You've got you've got the nucleus. There we go. So you've got the nucleus, and then around the nucleus, you have electrons in specific energy levels or shells. And these shells only accommodate so many electrons, right? For example, the first shell, the shell that is closest to the nucleus, and this is called n equals 1. That's the first, or what we call the ground state. This is killing me today. All right, that's the ground state. It can hold a maximum of 2 electrons. That's it, 2 electrons in the first shell. And then once it fills up, no more electrons can go in. And so electrons have to fill shells further away with higher energy, right? And so the first state, or we call the ground state, can only hold a maximum of 2 electrons. And then the second shell, we call n equals 2, it can hold more than 2 electrons. It can hold up to 8 electrons. And then it fills up, and then you have to go to the next shell, n equals 3, and so on and so forth. Now, when it comes to chemistry, we only care about the outermost shell, right? The outermost shell, the electrons in this outer shell are the electrons that are responsible for chemical interactions. And this shell is so important that it has a special name. It is called the valence shell. And the electrons in this valence shell are called valence electrons. All right. And then the electrons deeper down are what we call core electrons, but they're not important when it comes to chemical bonding. Now, the reason I bring that up is to go back to the periodic table of elements here. Let me see if I can get rid of. This is killing me. It's not helping. All right. Well, I'll just have to describe it, unfortunately. All right. So if we go back to periodic table of elements, the group, right, 1, 2, 3, 4, 5, 6, 7, 8 columns, that tells us how many electrons there are in the valence shell. So the period tells us how many shells of electrons there are around the atom, and the group tells us how many electrons are in the valence shell. All right. So for example, if I look at hydrogen, right, H, what period is hydrogen in? Could someone tell me? What period is hydrogen in?
1.
It's in period 1, which means there's only one energy level around hydrogen. And how many electrons are in the valence shell of hydrogen? Well, what group is it in?
1.
1. So
Good.
every element in group one, so hydrogen, and then underneath it is lithium, and then sodium is underneath that, and then potassium is underneath that, and rubidium is underneath that, and cesium is underneath that, potassium is underneath that. All have one electron in their valence shell. Now, lithium has two shells around it, the nucleus, but the outermost shell only has one electron. Hydrogen has one shell and it has one electron. Potassium has four shells, but the valence shell still only has one electron. Does that make sense? They are in different periods, but they are in the same group. And elements in the same group have similar chemical properties. All right. So that brings us to a couple of rules of thumb, if you will. So let's just talk about some basic rules of thumb here. All right. So some rules of thumb to understanding this. So rule of thumb number one. So all atoms in N equals 1 in the first shell. The first shell fills with 2 electrons. All right. So 2 electrons completely fills the first shell. All right. Now, beyond that, second, third, fourth, etc. Generally speaking, if you can get 8 electrons in all cells, all right, the atom will be stable. All right, it'll be happy. The major exception to that is the first, right? Because it's completely full at 2 electrons. But all the other shells are going to be stable when there are 8 electrons. And this is so important that these are referred to as the duet and octet rules. The duet and octet rules. If there is an atom that only has one shell and there are only 2, hydrogen and helium are the only 2 that actually have one shell of electrons. All the other have more, right? Because they are in periods 2, 3, 4, 5, 6, etc. Right? So hydrogen and helium are the only exception to all of the others, right? So these are happy when they have 2 electrons in their valence shell. That's called the duet shell. All other atoms are going to be stable if they can get 8 electrons in their outer shell, their valence shell, and that is referred to as the octet rule. And this is a basic rule that kind of governs the chemical activity of different atoms. All right. Now, these guys here in the middle, this purple in the middle, we're getting some lag going on here. There we go. All right. So the stuff in the middle here I don't know why it is not letting me. You're just killing me today. Oh, well. So everybody see the, there we go. In the middle there, those are called the D block elements, and they do not follow the octet duet rules. They are, think of them as like the super sexy swingers of chemistry. They are very wild and loose with their electrons, their valence electrons. So they don't follow the rules. So we're not going to spend a whole lot of time talking about them. All right. And then finally, most chemistry involves only the valence electrons. the outer electrons. All right. So before we take our next break, are there any questions? Because I know I just did a big information dump on you all. So are there any questions? Anybody have any questions?
No questions.
No?
No
Okay.
questions.
So during this next break, what I'd recommend you all do is go to Canvas, download that periodic table of elements I put in Canvas for you, because we'll be referencing it as we start talking about chemical bonding. All right. So let's see. It is 10:34. How about I see you all at 10:45? We'll come back at 10:45.
Sounds good.
Hey, Chris, quick question.
Yes.
Nothing to do with what we're going over in class. It is snowing like crazy up here, and they're releasing the kids early from school. We weren't planning on that, and I was expecting my husband to be able to pick him up, but my husband's still at work.
Okay.
So I may have to leave a little bit early. They dismiss at 12 today.
Okay.
So I just thought I'd let you know.
Yeah, we should be done before noon.
Okay.
So I'm guessing maybe another hour or so, and we'll probably call it.
All right. All right. Thank you.
No problem.
So I got something, Chris.
Yes.
So back to the table, when you were describing the hydrogen, you said the top number is the atomic number and the hydrogen is the atomic symbol. I didn't get the last part of the bottom number there.
Well, in this particular table that you see here in front of you, there is not that number, but that bottom number. Let me go to those notes. This one here.
Yes, sir.
Yeah, this is what's known as the atomic mass.
Okay.
Yeah. So hydrogen, because most of the mass is in the nucleus and there's one proton, it has an atomic of basically it's slightly higher than 1. It's like 1.001. So yeah, that's known as the atomic mass, and that's just in what we call AMU, or atomic mass units.
Okay. Sounds good. That's kind of where I was kind of lost there.
Perfect. No. Sorry for asking. Yeah, and that will become relevant a little later on in class as well. But yep. All
Okay.
right.
Awesome. Thank you.
Yeah, not a problem. Thank you. There we go. So let's go ahead and continue on. So what I want to do now is I want to actually start talking about how these valence electrons can interact between various atoms to kind of produce the chemistry and the chemical bonding that we see. So we're going to start talking about different types of chemical bonding next. So let's just start off anew. All right. So let's see here. Let's do the following. Let's take hydrogen. So how many protons does hydrogen have?
1.
1.
Good. So if we look at hydrogen, its atomic number is 1. Its atomic mass, someone asked about that, 1.001 is 1. That's not going to be super relevant for chemistry yet. So its atomic number is 1. So hydrogen has, so if we build a hydrogen atom, it has 1 proton. And how many electrons does hydrogen have?
1.
Electron. Good. And how many shells of electrons are there around the nucleus of hydrogen?
1.
1. And there's only 1 electron, so of course there's only going to be one electron in the valence shell because it's in group 1. So that's a hydrogen atom. That's a way of, oh, you guys can't see this.
No.
Or can you're not seeing what I'm seeing. Let's try this again. There we go. There we go. There. All right. So there's a hydrogen atom. So I've got one proton in the nucleus and one electron in the first shell, and there's only one shell. All right, so that's hydrogen there. So now what I want to do is I want to take a look at, oh, let's see here. Let's take a look at, let's take a look at sodium. So first, I'll just draw that there. So we look at sodium. Sodium is Na, of course, and it has an atomic number of 11. All right, so let's look at sodium. So the nucleus of sodium, how many protons does sodium have?
11.
All right, so I've got 11 protons. So how many electrons will I have?
11.
11, and those 11 electrons are going to be spread out in how many shells of energy? How many shells are there around the nucleus of sodium?
3.
3, because it is in the third period, the third row. All right, so the first shell, remember, it fills up with 2 electrons. And then the second shell, and remember we said after the first shell, all the other shells like to have 8 electrons for stability. So I'm going to fill those, and you can see how I pair the electrons up. The electrons like to pair up. All right, so that's 8, 9, 10. And then the third shell is going to have that last electron in it, 11. All right, so 11 protons and 11 electrons. That's sodium. Is everybody okay there with sodium?
Yes, sir.
Now, what I want you to do is I want you to look at chlorine. All right, so let's take a look at chlorine here. And what is the atomic number for chlorine?
17.
17. All right, so if we look at the nucleus, it has 17 protons. And how many energy shells are there around chlorine?
3.
3. It's in the third period, so there are 3 energy shells. 1, 2, 3. The first shell is going to have 2 electrons. The second is going to have 8. And then the third is going to have the remainder 8, 9, 10, 11, 12.
Chris, so no matter what in the third ring or second ring, the maxes out at 8, and then the rest just keep going further and further out.
No, we're just being very general here. But in general, beyond the first energy level, the shells are stable when there are 8 electrons in them. Does that kind of make sense?
Okay.
But once you get larger and larger, you have lot more electrons in those shells. So we're kind of hand waving a little bit, but I'm trying to simplify this just a little bit so you can understand at least the basics of what's going on here. So that is chlorine. Those are the 17 electrons of chlorine. Now, let me ask you a question. How many electrons does sodium want to have in its valence shell to be stable?
Needs one.
Well, it needs 8, right? Remember.
It wants 7.
Yeah, so I would have to add 7 electrons to sodium. Let's look at chlorine here. How many electrons does chlorine need in its valence shell to be stable?
1.
It needs 1 and it's stable. Its octet is met. Let me ask you a question. How hard do you think it is going to be to try to find and stuff 7 electrons into the valence shell of sodium? Do you think that's going to be easy or hard?
Hard.
It's going to be really hard. Yeah. So what if instead of getting a hold of 7 electrons, what if sodium were to give up this electron here in its valence shell? If it were to lose that electron in its valence shell, what would become the new valence shell?
The inner one of 8.
The inner one with 8, and sodium would be stable, right? But here's the thing. Sodium can't just give up that electron. That electron has to go somewhere. And let's just say that I take sodium and I put it close to chlorine. Well, what does chlorine really want to get a hold of?
That one electron.
It just needs 1 electron, doesn't it? So what can happen here is sodium can give up its 1 electron and it can give it to chlorine. So sodium here will give up its electron and give that electron to chlorine. So what happens is sodium will lose an electron and chlorine will gain an electron. Now, because chlorine has gained negative charge, right? There are more negatives than positives, right? There are now 18 electrons. And so the overall charge on chlorine becomes negative, right? Because it's gained that electron. What has happened to the overall charge on sodium, however?
Positive.
Becomes negative or positive.
Positive because it gave up an electron. So sodium becomes positive and chlorine becomes negative, right? Because sodium gave its electron to chlorine, right? And now what you have is you have a positively charged sodium that's attracted to a negatively charged chlorine, and they will come together and bond to form a molecule of what we call sodium chloride, or NaCl. And this is the first major type of bonding. When atoms that have either lost or gained electrons come together to form a bond, we call that an ionic bond. And ions are atoms that have either gained or lost the electrons. That is what an ion is. All right. And ions that have lost an electron are what we call cations. And they are positively charged. And ions that have gained an electron are known as anions, and they have a negative charge because they gained the electron. They gained a negative, right? And then when these cations and anions are dissolved in water, all right, we refer to them as electrolytes. So electrolytes are ions dissolved in water. And when ions bond, we call ionic bonding. Is everybody okay with that there? And
Yes.
furthermore, cool. Furthermore, atoms that tend to lose electrons, atoms that tend to give up electrons, are referred to as metals. So a metal is an atom or an element where the electrons are not tightly bound in the valence shell. And then atoms that tend to accept or gain the electrons are referred to as nonmetals. All right. So when we go back to our periodic table of elements, let me pull that up for you all. Do you see this this staircase over on the right side? There's this green and there's kind of this yellow staircase here. Oh, come on. Oh, this is insufferable. See if it'll let me. There we go. So you see this little staircase here? I just was able to draw on top of it. Maybe. There. All of the atoms, so the atoms that are close to that, right next to that staircase, are what we call semi-metals. But all of the atoms to the left of that staircase are called metals. So all those on the left-hand side are what we call metals. They tend to lose electrons. And then the atoms to the right of that staircase are what we call nonmetals. They tend to gain the electrons. All right. With the exception of these guys here on the far right. So the group 8 are what we call the noble gases because their octet and duet rules are met. So helium has 2 electrons and both electrons are in the first energy level, it's stable. Neon, 2 of its 10 electrons are in the first shell, and then the other 8 are in the second shell, so it's stable. Argon, its third energy level has 8 electrons, it's stable. Krypton, its fourth energy level, its valence shell has 8 electrons. Xenon, radon, and so on. So these guys on the far right do not chemically react with anything. They're what we call noble or inert gases. They're not flammable. They don't chemically react. They don't form molecules. They don't form ions, any of that, right? They are just gases that are minimally reactive with their environment, right? Everything else is reactive. It tends to either want to gain or lose electrons, right? Based on where it's at on the periodic table of elements. Is everybody okay there? Does that make sense so far?
Yep.
All right, excellent. All right, so moving on. The next thing that I want to talk about is when something becomes an ion, there is a name change that occurs. All right. And it only occurs when something becomes an anion. When something gains an electron and becomes negatively charged, its name is changed. So when chlorine gains an electron and becomes an anion, Cl minus, chlorine becomes chloride, right? When fluorine gains an electron and becomes negatively charged, it's fluoride. When oxygen gains an electron and becomes negatively charged, it's called oxide. Okay. When carbon gains an electron and becomes negatively charged, it's called carbide, and so on and so forth. IDE tells you that you're dealing with an anion. Now, cations do not have their names changed. When sodium loses an electron and becomes positively charged, it's still called sodium. When lithium loses an electron, it becomes positively charged. Let's move over to group 2, magnesium. Magnesium, because it has 2 electrons in its valence shell and 8 in the shell underneath it, it needs to give up 2 electrons. So it will become +2, it'll become +2, magnesium +2 instead of plus, right? Because it needs to get rid of 2 electrons instead of 1. It's still called magnesium though. Calcium underneath magnesium is the same. Calcium also needs to get rid of 2 electrons. It's still called calcium. Potassium just needs to get rid of 1 electron, and it's just K+, right? All right, but they don't get their names changed like the anions do. All right, so that's ionic bonding. Ionic bonding is where you have a gain and a loss of electrons, and then the ions themselves bond. All right, that's not the only type of bonding that we have, though. The other major type of bonding is something referred to as covalent bonding. And covalent bonding is, instead of gaining and losing electrons, there's a sharing. There's sharing of electrons. So electrons are shared. That is covalent bonding. All right. So for example, let's take carbon. All right, let's take a look at carbon here. Let me see if I can get some more bandwidth here. So let's take a look at carbon on the periodic table. So carbon is in, let's see, take a look at carbon. It has an atomic number of 6. So there are 6 protons in the nucleus. It's in, let's see here, period 2. So there are 2 energy levels around carbon. And there are, let's see here, it is in 4, right? So 1, 2, 3, 4 electrons in the valence shell of carbon. So that's kind of what carbon looks like. So carbon needs to get a hold of 4 electrons, right, to be happy. And if we go and we take a look at hydrogen, hydrogen has 1 proton and 1 electron. How many electrons would hydrogen like to have to be stable in its valence?
1.
1. So what we can do here is if I take carbon and I just draw the valence electrons, so I have a carbon atom, what I could do is I could take 4 hydrogen atoms, right? So here's a hydrogen atom with just 1 electron, hydrogen atom with 1 electron, hydrogen atom with 1 electron, and a hydrogen atom with 1 electron. So what you could do is the hydrogens and the carbon could share. So if the hydrogen came and it shared with carbon and carbon shared with hydrogen, right? Now that they're sharing, this hydrogen has met its duet rule, right? And then the same with this hydrogen and carbon sharing. So this hydrogen is now happy. And then this electron gets shared here. That's happy. And then these electrons get shared here, right? And that's happy. And now carbon is sharing 4 electrons with 4 hydrogens. And its octet rule is met. The hydrogen's duet rule is met. And now I have a stable molecule. And I have a molecule of CH4. 1 carbon sharing its electrons with 4 hydrogens. And when you have sharing of electrons, you have covalent bonds. That's what a covalent bond is. All right. And this can occur typically with nonmetals interacting with other nonmetals. So when metals and nonmetals interact, you tend to get ionic, you tend to get ions, but when nonmetals interact with other nonmetals, with the exception of hydrogen, hydrogen is kind of its own thing, it's special because it just has a 1 electron, you tend to get covalent bonding. So for example, if I take oxygen, let's take two atoms of oxygen here. So oxygen has, it is in 6, right? It is in group 6. So oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. It has 6 electrons in its valence. And so if I take that oxygen and I move it close to another oxygen, 1, 2, 3, 4, 5, 6. Well, these oxygens can share their electrons, right? So we'll share these electrons here. That makes 1 covalent bond. And then we share these electrons here, and that makes 2 covalent bonds. And now I have a molecule of oxygen that is double covalently bound, right? And both octet rules are met, and now I have a stable molecule. If I were to do that same thing with hydrogen, so hydrogen has 1 electron, the other hydrogen has 1 electron, right? So you can share this, you can share that, and that's just a single bond, right? And so that's a single covalent bond, like that. And you can even have situations where you get triple covalent bonds. For example, let's take a look at nitrogen. How many electrons does nitrogen have in its valence shell?
Wow.
So what group is nitrogen in?
Group 5.
Group 5, yeah. Group 5, and so you've got 1, 2, 3, 4, 5. So you've got nitrogen here, and then another nitrogen. 1, 2, 3, 4, 5. And so the same thing here with nitrogen. You'll share, share. 3 covalent bonds, and then that produces a molecule of nitrogen. 1, 2, 3 covalent bonds, like that. All right. So that's sharing of electrons, covalent bonds, right? Gain and loss of electrons where ions bond together is what we call ionic bonding. And then the other major type of bonding is something called metallic bonding. And that involves those atoms, those elements in the middle of the periodic table of elements. Those are called the transition metals. And essentially, like, things like iron, for example, Fe, it falls right in the middle there. It's a transition metal. And essentially with iron is you get these nuclei floating in an ocean of electrons. Their electrons are not tightly bound. Their valence electrons are not tightly bound. So what you get is you kind of have this ocean of loosely bound electrons, and then the nuclei of the metal are kind of floating in this ocean of loosely bound electrons. You get something like this. And so those electrons are able to move much more freely. And so they kind of act like an ocean. And that is what you see with metallic bonding. And that's why metals, because they either tend to give up electrons or the electrons are very loosely bound, metals are very good conductors of electricity. They conduct electrical currents because the movement of charge is what a current is, right? And so electrical current is able to easily travel through metals because of that. And metals, you tend to bend them, right? You can bend them, you can squish them into small filaments and rods, wires. They're very ductile. They transmit heat. They are very good conductors of heat as well. And that is all due to the fact that the electrons are not tightly bound, very loosely bound, right? Whereas other elements like carbon, for example, right? Carbon is not a good conductor because its electrons are not loosely bound, right? Carbon is not malleable, does not bend easily. It's actually very solid. When you have a bunch of carbon forming bonds, it tends to be very rigid, right? Certain configurations of carbon, like diamonds, right? Diamonds are carbon bound in a certain crystalline structure. It's very hard. It's not a good conductor. Does not conduct heat as well as metals, right? So hopefully you can see just how critically important the electronic structure is to determining not only the properties, but the kinds of chemical bonding that you can get. So is everybody okay there? Is everybody okay with that? Because that's just kind of the basics of chemical bonding. Everybody okay there?
Okay.
Can you go back up a little bit for the covalent bonding? It was the double.
What do you need?
There it is.
Yeah,
So
those are just examples. Yeah.
Right. So that's oxygen, right? You said?
Uh-huh.
Okay. And then when they're single, okay, now I'm seeing it.
Yeah, so this is a molecule of hydrogen, right? H2. This is a molecule of oxygen, O2, and this is a molecule of nitrogen, N2. Just showing how you can get, different types of bonding. Just some basic examples there. All right. Now, when it comes to life, most of life really comes down to just a few elements. Like the most important elements when it comes to the biology and chemistry of life really comes down to con. So this is somewhere around 90+% of life comes down to these four: carbon, oxygen, hydrogen, and nitrogen. These are the most numerous atoms, most numerous elements that we see in all of biology. And so we'll be focusing on them quite a bit. All right. Now, The next thing that we need to understand is covalent bonding. It's the sharing of electrons, but, and here's the big caveat here, this does not have to be equal. That is to say that the sharing is not necessarily equal. All right. And there is a concept known as electronegativity. And electronegativity is essentially how much does an element want to get a hold of an electron, right? That's a way of conceptualizing electronegativity. And when you have something that's very electronegative sharing its electrons with something that is less electronegative, the more electronegative atom or element is going to hold on to more of the electron. It's going to spend more time around the more electronegative. So for example, oxygen, right? And the further right you go on the periodic table of elements, the more electronegative you get. And that makes sense, right? Because those are the nonmetals that want to get a hold of electrons. And then the further left you go, the lower you get electronegativity until you get all the way to that first column, that first group where they're trying to give away their electrons, right? Sodium, and potassium, for example. So when you have a highly electronegative element covalently bonding to a less electronegative, you get something interesting happening. And the most important example of this is actually in the water molecule, or one of the most important. So water molecule is oxygen, right? And how many electrons does oxygen have in its valence shell again?
6.
6, right? 6 electrons. So 1, 2, 3, 4, 5, 6. So that's oxygen. And then we have hydrogen with 1 and another hydrogen with 1. And so what you can get is you can get this hydrogen shares with this part of the oxygen here. All right. And you get H2O, right? You get oxygen covalently bound to hydrogen. But oxygen is highly electronegative. So it is going to hog the electrons, right? It's going to share, but it's going to be like, you can have a little bit of electrons sometimes, but I'm going to take most of the time. And so if we were to draw a map of where the electrons are going to be around a molecule of water, it would look something like this. The blue is the density of the electrons. So it looks something like this. They're going to spend a little bit of time around the hydrogen, and it's going to be very dense around the oxygen, right? So what happens is this part of the molecule, because the electrons are spending more time around the oxygen, this part becomes partially negative, and then this part becomes partially positive. So that you have a separation of charge. And this is what we call a polar molecule. A polar molecule is where you have a highly electronegative atom covalent bonding to an atom that has very low electronegativity, such as oxygen and hydrogen. Okay. And so part of the oxygen becomes negatively charged, and then the other part becomes positively charged. And what this allows is this allows individual molecules of water to begin interacting. And this is something called an intermolecular force. All right. So it is not individual atoms that are interacting, but rather it is molecules interacting. So when you have a bunch of molecules of water, I take a bunch of molecules of water and I put them together, what's going to happen is the relatively positively charged hydrogens are going to be attracted to the relatively negatively charged oxygens, and the water molecules are going to begin sticking together, right? They're going to stick together. They get sticky. And that's why water is a liquid, right? Is because the individual molecules are polar and they are attracted to each other. The other interesting thing about water is, if I draw some more, let's do this. Here, let me just draw some more here. If I put an ion, I put something that's ionics. For example, I put a molecule of sodium chloride into that water. That molecule of sodium chloride will break apart, what we call dissociate. And it does. Remember, the sodium is positively charged and the chloride is negatively charged. The positively charged water will be attracted to the negative part of the water molecule, right? So the positively charged water, or positively charged sodium, will be attracted to the negative part of the water molecule, and the negatively charged chloride will be attracted to the positive part of the water molecule, the hydrogen part. And so you'll put that sodium chloride in, and then it'll break apart because the sodium wants to go toward the oxygen and the chloride wants to go toward the hydrogen. And you have now dissolved that molecule of sodium chloride. And that is what makes water so special. The fact that it is a polar molecule and it can dissolve other polar molecules or ions. And when we say that something can dissolve stuff, we call that a solvent. So water acts as a solvent because it is polar, and these intermolecular forces, right, dissociate ions like sodium chloride. And then you have individual sodium ions and individual chloride ions. Now, if you had a non-polar molecule where there is more equal electron sharing, for example, if I have a molecule of oxygen, two oxygen atoms covalently bound, double covalently bound, that's equal, right? That is equal sharing of the electrons there because they're both oxygen atoms. And so what happens is this is a non-polar molecule, and a non-polar molecule will not dissolve in polar solvent. So oxygen does not dissolve in water, at least very easily. And hopefully you're beginning to start to make some connections like, oh, this is why we need hemoglobin, right? We need hemoglobin to transport oxygen in our blood because our blood is mostly water and oxygen doesn't dissolve in water, right? But we don't need molecule to transport sodium and potassium and chloride because those are ions and they dissolve in the polar water of our bodies. It acts as a solvent, right? Does that make sense? Is everybody okay there? Does that make sense?
Yep.
Okay. And this particular intermolecular force that you see with water molecules is so special, it actually has its own name, and it is what we call hydrogen bonding. Where you have hydrogen covalently bound to a highly electronegative atom like oxygen. And it is the hydrogen bonding that holds water molecules together, makes water exist as a liquid at room temperature, and allows water to dissolve to act as a solvent to other polar molecules, but not nonpolar molecules. And what is the name we give molecules that get dissolved in a solvent? So if you do the dissolving, you're the solvent, but if you get dissolved in a solvent, you are called a what?
A solute?
A solute. There you go. So solute gets dissolved in a solvent, and a solvent does the dissolving. Does that make sense? Everybody okay there? So hopefully beginning to appreciate, holy cow, all the stuff about water's important, it's coming back. It's like, oh, this is the chemical basis for all this, right? This is a chemical basis for all this happening, the actual basis of the human as a biological system. Okay, so let's see how we're doing. What time is it? It is going on 11:30. I think what I'm going to do is I'm going to do a quick little exercise with you all, and then we're going to call it because we've gone over quite a bit today. So before I let you all go, I've got one little Padlet that I want to do.